we start today's talk. I am Dr. Nasir Maziz Mirza, and this is Introductory Nuclear Physics, and today's topic is the neutrons in the nucleus. What is a neutron? Neutron is a subatomic particle with no net electric charge. Neutrons are bound within the nucleus through strong nuclear force. In coming lectures, we will discuss in detail what is nuclear force, the strong nuclear force and the weak nuclear force. The nucleus consists of protons and neutrons, and both of them are termed as nucleons. The number of protons determine the element, and the number of neutrons determine the isotopes. For example, isotopes of nitrogen are the nitrogen 15 and the nitrogen 14. The nitrogen 15 has 7 protons and 8 neutrons. However, the nitrogen 14 has 7 protons and 7 neutrons. So you can see that the change of the number of neutrons is going to dictate the isotope nature, and the number of protons within the nucleus decide about the nature of the chemistry of the element. Let's briefly discuss the neutron's discovery. In 1920s, Rutherford postulated that there were neutral massive particles within the nucleus because the mass of the atom is larger. As we see, it cannot be just the protons. James Chadwick discovered neutrons in 1932. He bombarded beryllium target with alpha particles and produced neutrons that recoiled into a block of paraffin wax. Paraffin wax contains carbon and hydrogen in a complex molecular structure. But for a single carbon, there are 4 hydrogen atoms, and therefore so many protons are available. And the alpha particles were producing the neutrons that were recoiling in the block of the paraffin. The produced neutrons were knocking the protons within the paraffin wax. So measuring the proton emerging from the paraffin with the help of a Geiger counter, he showed that the neutrons have mass comparable to that of protons. If we look at the simple schematics of the experimental setup, then we see that the first is a polonium source, which is an alpha source. It emits alpha particles, and in front of that, the beryllium is placed. So the nuclear reaction takes place, and as a result, neutrons are emitted, and these neutrons travel towards the paraffin. So in paraffin, neutrons collide and scatter, and this scattering produces the protons. It is kind of sort of a billiard ball game in which the neutron hits the protons. Proton-rich environment is paraffin, and these protons are really going to the ionization chamber or a Geiger Muller tube like arrangement, where they are producing clicks and they are detected. Let me briefly go through further what happened really in the discovery of neutrons. In 1930, Walter Bothe and the Baker found that alpha particles emitted from polonium, they, when fall on certain light element such as beryllium, then they produce very penetrating radiations, and eventually we came to know that it was alpha N reaction. Alpha particle is the incident particle, and the emitted particle is neutron. In 1932, Irene Julio Curie and Frederick Julio showed that this unknown radiation, which is falling on the heterogeneous compound, it is ejecting very high energy protons. So they concluded that something is going on, the neutron or something is hitting and the protons are getting out. They calculated originally the energy, and it was not really correct energy distribution that was possible, and therefore their idea was rejected. They said that it is a very strong gamma rays, and that idea was also rejected. In 1932, James Chadwick showed that the gamma ray hypothesis of the paper written by Curie and Julio was really not the correct version. And the new radiation that was coming out was uncharged particles, approximately that of the mass of proton. And that led to the discovery of the neutron. If we go through the certain properties of the neutrons, and we see that the free neutron is unstable, and outside nucleus it will decay. The decay of the neutron involves basically a weak interaction, and it is associated with a quark transformation. A down quark is converted into up quark, and that's what we know very well after the quark theory came and the weak interaction was thoroughly explained. The beta decay in this regard creates approximately a lifetime of 885.7 seconds with plus minus of 0.8 seconds. So it's roughly 885 seconds that a free neutron can live without nucleus. They cannot be stored long without the nucleus, and outside nucleus they are going like this. A neutron is produced, then a neutron converts into a proton and electron, and the anti particles or the idea of the neutrino carrying energy later came because it was very difficult to explain the beta decay's energies, and the energy spectrum was a continuous spectrum. It was not a discrete spectrum, and therefore it led to the discovery of this neutrino associated with this electron and the antineutrino. The mass of the neutron is slightly larger as compared to the proton, and the mass in terms of energy is 9.565 million electron volts per c square. This is the current unit for the mass. Neutrons have spin half. So they are spin half particles, and according to modern statistics, they obey the Fermi-Dirac statistics. So they are fermions, and the fermions obey Fermi-Dirac statistics, and the spin half particles have certain properties that are really to be obeyed by the Pauli exclusion principle as well. Neutrons have no electric charge. Therefore, they remain neutral. However, the neutrons have magnetic moment. They have certain magnetic moment, in spite of the fact that they don't have the net charge, electric charge. They have magnetic moment. The neutron spin is really very, very important. The spin quantum number S for the neutrons is half. So they are spin half particles. Their angular momentum is basically really can be estimated with the help of this equation, which states that it must be in the chunks of h cut multiplied by under root of s into s plus half s plus 1, and s is half. So angular momentum is really quantized, and its value is half. Particle with the angular momentum have magnetic moments. So its magnetic moment is this. Although the net charge is not there, but this angular momentum's presence dictates. So basically the spin is creating the angular momentum, and the angular momentum results in the moment, the magnetic moment. So neutron is really, now we know, they are made up of quarks. They are electrically charged particles. The magnetic moment of the neutron is ultimately coming as a result of the spins of the individual quarks, because they have the orbital motions and they are really producing. So although the net charge is zero, but the spinning quarks do produce the angular momentum and the moment. If I recall, the wave-particle duality, de Broglie has already spoken on this, that every particle has an associated wave. So the neutrons, since all matter is wave-like nature, therefore the neutrons also have the associated wavelength, and they really show the direction, and they have the wave-like properties, and therefore they can show this, that energy is related to the frequency, and the frequency is related to the wavelength, and the wavelength is given by h divided by m into v. M into v is the momentum, the linear momentum. Therefore, there is wavelength and there is frequency, and its energy relation can be estimated through this. The neutrons have wave numbers. Since they have the wave, so the wave also have this wave number, which is defined as how many waves are really within the 2 pi. So 2 pi divided by lambda is the defining wave number. Strictly speaking, this wave number is the angular wave number, because it is caused by the angular momentum of the neutron. And the energy in terms of the wave number is given as h cut square multiplied by k square divided by 2m. And that's how the neutrons are expressed in the quantum mechanics. Basically, it is the wave which has a wavelength and the wave number. Neutrons really have plane waves. Constant frequency wave, whose wavefront surfaces show a constant phase, are infinitely parallel planes of a constant amplitude, which is normal to the wave vector k. And if we want to write down in the quantum mechanics, we can show that the physical solution for the neutrons' plane waves can be expressed in the form of this u, which is function of the position vector x. It is not really the x coordinates, it is the x vector which has the x direction, the y and z, and the t, and it is given as a multiplied by e to the power iota times k dot x. The k is a vector of the wave vector, which is perpendicular to the wave front, which is shown here. And the omega t, the omega is the angular frequency and the t is the time. And the general form for the such plane waves is given by a constant multiplied by cos times k dot x minus omega t, and it is the physically realizable wave. The k is the wave vector and the t is time, omega is the angular frequency, and we are assuming a real amplitude a, then it is the case, and the neutrons really do have the plane waves because they have shown the diffraction. Let's talk about the current situation in which the neutrons can be produced with the help of the small neutron sources. And the first and the foremost source available is through the isotopes, which can have the spontaneous fission. There are certain isotopes that undergo spontaneous fission with the emission of neutrons. For example, one fission source is the isotope californium-252. It is a spontaneous fissionable source. It emits neutrons, and typical californium-252 neutron source can emit 10 to the power 7 to 10 to the power 9 neutrons per second. It has about 2.6 years of half-life, and it is only produced in nuclear reactors. Then there is americium beryllium type neutron sources that were originally used to produce neutrons in the discovery of the neutrons. Americium-241 emits alpha particles. So this alpha, if it's going to hit the beryllium, then this nuclear reaction takes place. The combination of the helium and the beryllium nucleus produces C13. A C13 type thing is such that it is unstable, and it then changes into carbon 12, and then a neutron, and some energy is released. The energy is the Q value of the nuclear reaction. The source strength of these sources are generally measured in terms of the alpha sources. The larger the alpha source, the larger will be the americium beryllium-like neutron source. So, for example, if we have 1 Curie americium beryllium source, then this 1 Curie source is basically due to 1 Curie americium-241. Let's briefly discuss the nuclear reactions and how, because I have already shown you one nuclear reaction, I must brief you about the nuclear reactions. There is a theory which is termed as compound nuclear theory. We'll talk more about this in coming lectures when I discuss the nuclear shapes and sizes and how the binding of the nucleus takes place. One idea is the compound nucleus, and a nuclear reaction is basically a two-stage process which produces first a relatively long-lived intermediate nucleus, and then it decays into the parts that are really more stable. So a bombarding particle first loses all of its energy to the target nucleus, and then it becomes integral part of the unstable nucleus. This nucleus is termed as the compound nucleus. The compound nucleus is really unstable. Then the compound nucleus disintegrates into two parts. One is the ejected small particle, and then there is a product nucleus. So if we have X nucleus, the target nucleus, and A is the particle beam which is hitting this nucleus, and then we produce a Z star, something which is unstable, and then we get it converted into Y, a relatively stable nucleus, and then B, the small particle which is ejected out and going away. The compound nucleus is really the unstable, and this is this idea, the way it is generated is the compound nucleus theory, and it was put forth by Niels Bohr, and still very useful for explanation of fission and fusion types of reactions. The formation of compound nucleus then guarantees that the other type of the nucleus will be produced and something will be getting out. In a nuclear reaction, there are several things that are conserved. And if we go one by one, first conservation is that of the mass number. The mass number is the total number of the nucleons that are present in the nucleus. This number remains fixed. So the sum of the reactants mass number must remain the sum of the product mass number. The original mass numbers and the final mass number remains the same. Then we have the conservation of atomic number. Atomic number stands for the number of protons or the number of charge, that is the total charge. Sum of the reactant of the total charge must remain same. This charge is not going to go away somewhere. They are there. The conservation of energy is also one important feature. It demands that the total energy of the reactants must remain equal to the total energy of the products. So the total energy is the sum of the rest mass energy and the kinetic energy of the nucleus in all these nuclear reactions. Whenever we are calculating the total energy, we must take into account the rest mass energy and then the kinetic energy. We will have several examples in coming lectures where we show this. Linear momentum is generally conserved, and it demands that the total vector sum of the reactant linear momentum must remain same before and after the reaction. The angular momentum conservation is also desired, that the total vector sum of the reactant's angular momentum, which includes the spin, must also remain the same as that of the product. And the one another important idea is the isospin, which is demanding that the total vector sum of the reactant's angular momentum, the vector sum of the angular momentum, must also remain same. And this idea is called isospin conservation. A nuclear reaction can be processed if all these conservations are really obeyed. Let us look into certain details of the neutrons reacting with the nucleus. If we have produced a source of a neutron and we want to use neutrons for certain nuclear reactions, we have seen that the neutrons generally do not really show any reaction with the electrons outside the atom. They have tendency to have the reactions within the nucleus. The first is the elastic scattering. It occurs when the no energy is transferring between the target nucleus and the incident particle. For example, this lead PB208 is hit by the neutrons, and they are elastically scattered. Energy of the scattering is conserved. Then the neutron just scatters away, and the lead nucleus remains the lead nucleus. Inelastic scattering is the case which transfers the energy. When the energy is transferred to the product, for example, the Ca40 is hit by the neutron. You can see this is the incident particle. The N is the incident particle, and Ca40 is the target on which it is hitting. When it is hitting, then it creates a compound thing, and then that compound thing changes into Ca40 star, which is the different nucleus, because it is an excited state now. And when it will de-excite, it will emit certain form of energy. And the N dash is also the neutron which is produced, which is coming out, and it is not the same neutron. It is with the different energy going in certain different direction, and therefore this reaction is the inelastic scattering. Then there is a capture reaction. Both charged and neutral particles can be captured. The nucleus can capture them, which means that once nucleus has captured the particle, it will only emit the gamma rays. Neutron capture reactions are very important, and one important nuclear capture reaction is shown here. It is U-238, which is hit by the neutrons, and it is producing the U-239 and the gamma ray. So the product is U-239, and the gamma ray is emitted because it was, when a compound nucleus was formed, it de-excites and by emitting a gamma ray. So the neutron is captured, and now the total number is changed, but uranium is uranium. 92 is same, the Z number is same, the charge is the same. Eventually, this is unstable. It will decay into certain things, and it becomes plutonium-239 eventually, and that we are not really showing here. The transfer reaction is one important reaction in which the absorption of the particle takes place, but the compound nucleus emits one or more particles that are different, and it is a transfer reaction. For example, NP reaction is a transfer reaction. N alpha reaction is a transfer reaction. ND reaction is a transfer reaction. And T is a transfer reaction. N is the incident particle which is hitting on the target, and the P is the particle which is leaving the system, and the other nucleus is the product nucleus which is produced. So transfer reaction is accompanied by the emission of one or more particles. Some other type of nuclear reactions are also of interest in the nuclear physics, and one interesting reaction is the fission reaction. Nuclear fission is a reaction in which a neutron hitting the uranium-235 splits it into this lighter nuclei. More than one particle is as a product is produced. Two or more particles are produced, and we have seen that 2 or 3 neutrons are also produced. So those 2 or 3 particles that are eventually produced are called fission products. So the fission process is in which a free neutron or a photon will hit the U-235 and will release a large amount of energy and will produce 2 or 3 neutrons and the fission products. These 2 or 3 neutrons are really responsible for carrying the chain reaction, and that's why the fission reaction has become immensely important, because it can start flowing, because one neutron is lost, but the 3 neutrons are produced, and those 2 or 3 neutrons can hit again and will keep on increasing the nuclear fission reactions. So to find and estimate how the reactions are really carried and what neutrons can do, we have to learn how the number of reactions are taking place. And one interesting quantity is the microscopic cross-section. Microscopic cross-section for the nuclear reactions, particularly in the case of neutrons, is really interesting. So microscopic cross-section is basically interaction probability. It is the likelihood of a point projectile like neutron hitting the target area, the cross-section, and how much target area a point projectile sees. Each nucleus is thought of being surrounded by certain characteristic area, which may be larger or smaller than the area of the physical area of the nucleus. The measurements are done in the terms of areas, and the smallest term used is barn, which is 10 to the power minus 28 meters square, or in terms of centimeters, one barn is equal to 10 to the power minus 24 centimeters square. It is the cross-sectional area of the nucleus that is seen by the target hitting neutrons. The cross-sections are different. So neutron sees different cross-sections for different processes. For example, if it is scattering, it sees different area. If it is absorbing, it sees different area of the same nucleus. It sees extremely different for fission. The cross-sections are not constant quantities. They are dependent on energies. The incident neutron energy, if you change, the slow neutrons or the fast neutrons are hitting, then the cross-section change, which means the possibility of the reaction changes, the probability of the reaction changes, because interaction probability is proportional to the cross-section seen by the nucleus. The nuclear cross-section, if I try briefly to explain this in terms of a real reaction, then we can guess a beam of particles that is really hitting a thin sheet of material, which is containing n number of nuclei per unit volume, that is n per centimeter cube, and the thickness is x or dx. The area is A, which is hit by the beam. So if one particle interacts only with the dn number of particles throughout this as being removed from the beam and passing through the slab of the thickness dx, then we can find out the effective area. The total number of the nuclei present can be estimated with the help of this. N is the total number of particles per centimeter cube or per unit volume. And if you multiply by dx multiplied by A, this is the volume exposed, then we get the number, the total number of the nuclei. And effective area, which is available for the reaction, then is n dx into A, this total number of nuclei, multiplied by each nuclei C, the sigma, the microscopic cross-section. This is the area seen by each nuclei. So this is the total effective area available for the reaction. So interacting particles per unit, the incident particle, is this total divided by the target area. And we see that this is given as n multiplied by sigma into dx. And this is what the rate, the interacting particles per incident particles are. And this is being removed, therefore the negative sign is there. I can further find out the macroscopic cross-sections ideas with the help of this equation. But let me tell you that once we have produced this kind of a product, n into sigma, the number of particles per unit volume multiplied by the cross-section seen by individual neutron, then this is the macroscopic cross-section, and it is macroscopic cross-section. It has a unit of 1/centimeter. It is also called mean free path proportionality, because 1 over this macroscopic cross-section is the mean free path. As we have already seen, this number of particles that are removed from the beam per unit particles is given by n into sigma into dx, and we can integrate it from initial values to certain value in time, and for 0 to x distance of a slab. And then if we integrate, we get n over n naught times e to the power minus n sigma into x. N sigma, we can say it is a macroscopic cross-section, so we can write it in the capital sigma. Capital sigma multiplied by x. So we can see that it is the number which is removed from the beam is exponentially changing with the distance. So the particles that came at the beginning of the slab and the particles that are at the end of the slab are really different, and they are decreasing by this exponential curve. People have shown the measurements, through measurements, experimental measurements, the cross-sections are really, really different for different materials. And they are energy-dependent cross-sections. These are the microscopic cross-sections. Here I show you that these cross-sections are the experimental cross-sections. They are fitted with the curves, and they show these different behaviors. Let me briefly tell you that this is evaluated nuclear data file, which has been produced with the worldwide help, and all cross sections are reported there, and the experimental cross sections are placed, and then a fitted curve is produced. The cross sections are in terms of bands, and this is a logarithmic scale on which it is shown. On x-axis, the energy is also shown in the logarithmic scale, and it is MeV scale. Therefore, 10 to the power minus 6 multiplied by MeV will 10 to the power minus 6 multiplied by MeV will make it 1 electron volt. So roughly speaking, here is the 1 electron volt, and the less than 1 electron volts are here, and the more than 1 electron volt are there. This is 10 million electron volts. The regions are called the cold region for the neutrons. The neutrons in these energy ranges are called cold electrons. The neutrons in the energy range of 0.1 electron volt and less are called thermal electrons. And the epithermal electrons are those lying with the 0.1 to 1 electron volt energy range. And the fast electrons are which have energy higher than 1 electron. It is in tens and hundreds and thousands of electron volts, and less than the million. 10 to the power 7 electron volts is the possible measured in this graph, the highest possible neutron energy. As you can see, these cross sections are different for the different types of the reactions, and I will later discuss them. But the regions are according to the energy, and their broader names are grouped as cold, thermal, epithermal, and fast neutrons. The resonances are these sharp changes are the resonances, and they occur at the high energy. And the constant plateau are the scattering cross section. The fixed values are also shown, and 1 over V behavior is this called the absorption related behavior near the nucleus, and the probabilities are as 1 over V behavior. They call it the straight line decreasing in this kind of a graph. So there are 3 names for these curves: the resonance region, the constant or the epithermal region, and the 1 over V behavior of the 1 over V dependence of the cross section. Let me also very briefly talk about this cadmium. It is generally used as a shielding material, and in a current nuclear system, they are the absorbers for the neutrons, because they have shown very high cross section for the absorption. This blue curve is the absorption, and the thermal cold and the thermal region shows this. Before this 1 resonance value, this is the behavior, and the resonances are very, very small as compared to this strong absorption. You can see the cross section is about 10 to the power 6 bonds, very high cross section in the cold and the thermal region, and in the epithermal region, and in the fast region it has a resonances. So this is a good shielding material if the neutrons are in the thermal region, or they are epithermal neutrons, or if they are cold neutrons, then this kind of material is the best material. So cadmium, boron, gadolinium, the lithium-6 are really termed as great absorbers or the control materials for the nuclear reactor systems. They scatter strongly, they diffuse strongly, they also absorb strongly. And here we show the elastic scattering curve and the absorption the curve. And they are really very good absorbers, and that's how the neutrons have come to their use in the current nuclear physics. And here I stop the further discussion on the neutrons. We will further use the neutrons to understand the nucleus. We have seen that from the time of the Rutherford scattering, the scattering experiment is really helpful to tell us about the shape of the atom, the shape of the nucleus. So neutrons are really very, very fine for particles that are being used to study the shapes of the nucleus, and how the smaller or larger nucleus is behaving, and how the nuclear reactions are taking place. The discovery of the neutron led to the further discoveries of the nuclear reactions, the elastic scattering, the formations of the shapes, the form factors, the waves associated with the neutrons, and the diffraction. So in coming lectures, we will discuss how the shape of a nucleus are studied, and how the formation of nuclear reactions do take place, how people are using these for the further studies of the factors and the inner details of the nucleus. Thank you so much.